Esta conferencia comenzará a grabarse.
The fourth webinar from this technical series. Today is Phil with us. Phil Benghiat is our colleague that will conduct this webinar. We announced previously that was or will be done by Simon Scholl, but Simon now it's in Russia attending one of our projects. It's impossible to attend in the same time to this webinar. So Phil is our expert in hydraulic balance and in GoldSim model. So he will conduct that webinar. So I hope all of you enjoy it. And after his presentation, you can send us or asking the questions you know. So for those who are not familiar with Phil, he's one of our senior hydrologists and hydrogeologists. He has over 10 years professional experience across a broad range of mining projects, specializing in GoldSim, water balance and chemical mass balance modeling, and surface water management. He has been the architect of GoldSim models for a range of mine sites at the stage of development, spanning pre-feasibility through operations and into closure. His experience in surface water management includes hydrometric network design and installation, rainfall analysis, and rainfall-runoff modeling, and outline design of surface water conveyance channels and sediment retention ponds. He has worked on projects across a range of climatic conditions, including mine sites in Zambia, Eritrea, Mali, Mauritania, Ghana, Macedonia, Indonesia, Peru, and Dominican Republic. So Phil has a lot of experience worldwide and a good knowledge of what a mine needs from a good hydraulic balance and how to set up in a numerical model that we use or is very extended use in the mining companies in GoldSim, and try with that tools address the main companies in how to manage best the water from fresh water, how to manage contact and non-contact water and reduce the impact to the environment, reduce the need of treatment water, and at the end reduce the economics for the project. So Phil, that's the summary from you. So if you are happy, you can begin with the webinar. So please put all of your micros on mute and try to follow this webinar. Thank you.
Thanks very much, Eduardo, and thanks everyone. I'll run through the presentation today about surface water management for mining operations and applied water balance modeling. I'll turn off my camera quickly whilst I do this, just to save on bandwidth. Okay, so so today I'm going to talk about essentially like the initial assessment of surface water management requirements. So starting with the conceptual model and then the sort of things you need to consider that drives the surface water management on a mine site. After that, the infrastructure options available that's typical on a mine site for managing surface water. The criteria to which you design these structures to manage the risk of surface water issues, data collection, and the analysis of the data, and then a big focus on water balance models at the end. So starting with the conceptual model, this really is absolutely key to get as correct as possible, and it's the first thing we think of when we go on a project. You from the very beginning you bring together all the information you can, and it guides what data you need to collect, what studies need to be done for managing surface water. So should as a minimum include consideration of the climate, the topography, the pit, that's the mine design as well, where the pits are going to be, the waste rock dumps, the geology and hydrogeology, land cover and operations. So really try and understand how the surface water regime works on site. And with a strong starting point, a strong conceptual model, it's quite easy then to identify the surface water management requirements, and start to anticipate issues that surface water will cause on site, or impacts on surface water that mining will have. And at first it's a simple conceptual model. You do what you can with the data you have, but you keep on revisiting it and keep on questioning it and analyzing the data and running models, and the conceptual model will just get stronger and stronger as you go. But it's really important to understand the system on site, and no amount of modeling and computer exercises can replace that fundamental understanding of the surface water regime on site. So the sort of initial considerations for determining what surface water management is needed on site, the key drivers as such. So things like consideration of safety. Is there surface water flows there's going to be a danger to people, inundation of work areas, flooding of the pits, consider, and you'd need to consider things like diversion channels around pits to convey peak flows and flood flows. Other considerations: environmental and social impact. Is the mine impacting the water quality, the surface water quality, and that's could be released and cause environmental impact, or is the mine causing a loss of catchment and impacting water supply downstream to communities? And things that you consider then is, do you need to work with water storage and treatment options on site? And another one, regulatory compliance. So the regulator may set minimum discharge requirements and have water quality standards for discharge from the mine site. Now these three are kind of the surface water management strategy has to address these. There's no consideration of safety is paramount if water getting into your pits is going to cause an issue for people working there, or if you've got say underground operations that have commenced beneath an open pit, for example, block caving, and you get flows into the pit. The surface water has to be managed, and the infrastructure has to be put in place to manage that. So, and same with environmental and social impact downstream, and surface water management has to be undertaken to meet regulations. But there are other considerations. So operational considerations: will surface water issues cause downtime? Certain areas getting flooded periodically and shutting down the process. What issue does that cause? And things like the benefit of maybe keeping contact water and non-contact water separate to minimize on things like treatment requirements. Other things like social factors, but specifically the perception of social factors. So for example, all the science can be done perfectly, and there can be no issue with any kind of downstream issues from the mine site in terms of water quality and quantity, but the perception amongst the community may be that it's not safe. For example, there could be a storage pond with contact water kind of upstream of a community that's well stored, but completely understandably there's people that's uncomfortable with that being in that location because it feels like a threat, even though it's completely safe. And so that sort of thing needs to be considered. And the big one, the appetite for risk. So often set at a corporate level, but how willing is it acceptable for a pit to flood every 50 years or every 100 years? You know, what is that appetite for risk? And all that is based on a cost. So those latter ones are kind of you know, you do trade-off analysis of cost. So for the operational considerations, you know, is the cost of pit flooding and the pumping requirements to remove, say, a 100-year event actually less than the cost to build a diversion channel around the pit to manage a 100-year event? You know, or separating contact and non-contact water, is the cost to keep them separate more than the treatment cost to combine the two water streams? And again, the social factors like the cost of moving the contact water pond or diverting, you know, flows that could have the perception of being impacted more than the cost to sort of engage with the community and fully educate and explain why it's a safe method. So some coming out of this conceptual model and those drivers and the considerations, some surface water management options, you know, can start to be discussed and considered. So outside of the pit, there's you know, what surface water needs to be managed. There's runoff from upstream natural catchments. Does this need to be diverted around mine facilities, you know, to protect them from extreme flows, and also just to keep that water quality unimpacted and not mixing with water generated on site? There's also the management of surface water generated within the mine site. Does that need to be captured? Does that need to be conveyed somehow, again, you know, to protect the mine facilities from extreme flows? Does it need to be stored and then sent off to treatment because the water quality might be impacted? And consideration of things like sediment as well. And then even after consideration of these two, you know, some systems could be considered for these two that solve all the issues, but the other consideration is also the impacts downstream. So, you know, it may be that you know, it's not an issue to divert flow around the pit and around the mine, but does that diversion of flow increase flood risk downstream in you know, potentially in communities? Or does the mine itself, the removal of catchment and potentially using surface water as a water supply for mining, does that impact the base flow to the rivers, especially in places where you have strong dry seasons? And is that impacting any surface water supply downstream, or, you know, surface water ecology in rivers, and also impact on water quality? In-pit surface water management options. So, you know, this is very much important for geotechnical stability. There's a lot of failures due to surface water infiltration along the pit slopes and the associated increase in pore pressure. There's runoff, you know, from precipitation from the slope itself, runoff from the crest above the slope. So that's just the near pit area, you know, coming in, as well as shallow subsurface flow. You know, could be from a alluvial deposit or something at the top that has increased recharge and is coming into the pit. Uncontrolled groundwater seepage. So yeah, again, the alluvial seepage faces higher up in the slope. And there's some good pictures here, you know, showing that sort of uncontrolled seepage. There's no concentrated area of flow. It's just coming into the pit. And then also controlled groundwater inflow that may be from wells or horizontal drains, and it's controlled in that the groundwater is controlled to discharge into the pit, but there needs to be some surface water structures to convey this water to surface water management systems. So then there's so some structures that could be considered for surface water management. I mean, conveyance channels, external from pit. So, you know, are large scale diversion channels needed? So this is like if you're unfortunate enough for a pit to be, you know, in the path of a river and a whole, you know, river needs to be diverted, and that's, you know, a very big piece of planning, engineering, design, and big cost. There's also more local diversions, just capturing small catchments upstream of the pit, you know, requiring less large structures. And interception trenches or slurry walls, and that's sort of close to the pit to intercept even things like the shallow subsurface flow that's infiltrated near the pit crest. And then within the pit, you can have drainage channels on upper benches that are likely to be more permanent and can be, you know, quite well designed, and more money going into actually constructing them and making sure they last, you know, permanent to semi-permanently. And then there's more short-term drainage. So on the lower benches, that is a very dynamic environment, constantly changing, and the pit being deepened, and you know, these are just sumps and you know, simple grader cut channels or berms being pushed around, or sumps being dug to manage water, and it's much more dynamic and less planned. So some channel designs, I mean, this is in general for diverting water, but I guess specifically for haul roads here, you know, the classic trapezoidal channel that can be engineered and sized to convey the flows, the design flows that need capturing and diverting. But also, you know, you can use things like the actual crossfall of the haul road. So for routine events, you have a graded cut channel that can carry the water away, and haul trucks can continue to use the haul road, no problem. And then for extreme events, the haul road itself gets flooded, but the water is still managed and conveyed. So, you know, maybe haul trucks can't be used for that short, you know, the occasional period of extreme rainfall events, but it is a managed flow, and it's easy to maintain. It's easy, a grader can come and clear any sedimentation, and it's easy to manage, and it's low cost. And then, you know, for something where routine flows are actually quite significant, and a grader cut channel's just not large enough, you could do a mix between the two end members. So you can have a smaller, properly engineered channel to convey the routine rainfall events, but during the extreme events, it can fill and spill over into the haul road, and again, the haul road's used itself to convey the water. So just some images of this that is hopefully familiar as well from previous talks, and you see the crossfall sending it into the graded cut channel, and again, it can just be periodically cleaned to make sure it's always free and able to convey rainfall events. This is an image of uncontrolled flow, and it's coming down. It is being collected here, but around this corner, it's kind of uncontrolled across the road, which isn't ideal. So, you know, thoughts around putting in culverts, and, you know, or potentially design of some collection areas on these pit benches and pumps to remove the water. And just some examples of storage options. You have potentially flow attenuation ponds if peak flows are an issue, to store and then more slowly release the flows when you get peak events, or capture of contact water that can make sure there's no release to the environment or downstream and can be sent to treatment or managed in more passive systems. And then also water supply, the thoughts of impounding water as create some kind of reservoir for water supply purposes. And in pit, typically pit sumps, sumps on the pit floor. You can have staging ponds, staging sumps on benches that can collect water that's generated on pit slopes, but also can be used to as a transition point of water being pumped from the pit floor to the pit crest and away from the pit. And then sumps on the pit edge, that's the final point of discharge from the pit, and then can be pumped off to where it needs to go. And all these things need to be thought of as how they link together, how they all respond to different rainfall events, and what happens if a pump fails in one of the system. What's the knock-on effect down between all the sumps. So once the structures are kind of decided upon and it's kind of known what needs to go where, it's the next thing that needs to be done is defining the criteria for what sort of events they need to manage. And so the design criteria should be based on, what is the consequence of failure, and this relates to the drivers in one of the first slides. So, if a diversion channel were to fail, what would happen? Would there be loss of life, or would there be just 1 day of non-operational time? And that basically that risk assessment allows the design criteria to be set for surface water management infrastructure. So, one of the considerations for setting design criteria is how long is the infrastructure required for? So, is it just short-term construction? So, for example, construction, you're less likely to have an extreme event during the construction period, and then the cost of building something quite substantial for it to only be a temporary measure, is it worth it against the risk? And then operational, it's going to be slightly longer term, life of mine, and again, it's another trade-off of the risk of the infrastructure failing against the cost, and then closure, which is obviously permanent. That is another consideration again for you're guaranteed to have a 100-year event in that closure period, and you need to consider the impacts of that and whether it needs to be designed for. And a big consideration is how to operate these structures. So is it possible to maintain them, especially in something like closure? If it's going to silt up and you can't clear the sediment, and within a few years it's going to be massively impacted and blocked with debris and full up of sediment, something like ponds or or diversion channels, it's not worth building. And the big philosophy is, if you cannot maintain it, then do not build it. That's absolutely key to these things. Something that's maintained that may not be as on paper as well able to manage surface water is far more effective than something that will just fall into disrepair. So some general examples. So yeah, for conveyance channels, at least for construction, consideration of designing them to convey 2 to 20 year return period storm events. Operational, we'll be thinking slightly longer term, possibly designing the channels to convey 20 to 100 year. Closure again, which is permanent, greater than 200 years, and then critical infrastructure. And again, this is where failure will result in loss of life and unacceptable impacts, and it's just not a consideration. It cannot fail, and there you'd want to design to the PMP event, the probable maximum precipitation event, resulting in a PMF event, the probable maximum flooding. And this is key on things like TSFs, where we've seen the consequence of failures, and water just has to be managed correctly on these, and all the way through closure. And it just has to be designed to never ever fail or be an issue. And these are rules of thumb, but it really is site specific how these get set. So, for example, worked on a few places in West Africa, for example, and one there's a which is becoming more frequent is block caving, underground mining underneath open pit operations, and there's no, once the cave propagates up into the base of the pit, and the base of the pit starts to collapse, the access into the pit to manage any surface water inflow is gone, and anything rainfall falling onto the pit will make its way into the cave zone, and then ultimately into underground workings. And it's just imperative that surface water generated outside of the pit is diverted around the pit crest and isn't able to enter the open pit floor, because if that were to happen, that would all end up underground, and is risk of mud rush and all kinds of problems will result from it. So in that situation, that this consideration of designing pit diversion channels to greater than 100-year return periods, because even that is considered too high a risk to build. Whereas at another site, is fortunate enough that there was an old pit that was no longer operational immediately upstream of the operational pit, and when designing the diversion channel, even it was the option to spill extreme events into the non-operational pit and then slowly dewater that over a period of time, meant that a spillway from the diversion channel could be set at quite a low level, meaning that extreme flows would spill into the upstream pit, and so only routine flows needed to be diverted around the operational pit. So the new diversion could be designed to just a 5-year return period event, with anything higher than that going over a spillway into an upstream pit. So it's very much site specific. So data collection. So this is driven by the conceptual model and the surface water management requirements. So again, what infrastructure is going in that you need will drive what data you want to collect. So designing conveyance infrastructure with small catchments upstream, those flood flows are going to be sensitive to short intense rainfall periods. So a 30-minute rainfall event even could define your peak flows. So data should be set up to capture rainfall and flows on that at that frequency. And storage ponds, again, it might be a single event storage ponds if you're trying to attenuate flow, slow down flow from that peak event. So again, looking at short duration rainfall events, but it also may be a function of the flood flows, may be a function of antecedent moisture conditions and a very wet season or wet period, wet month, and then a moderately large rainfall event at the end of it. That might drive the peak flow. So again, collecting data on that sort of frequency is important. So the daily level might tell you that, and certainly for things like water supplies that is defined by long periods of drought, data on a 30-minute level isn't as important as just having that daily to weekly data set that will define a particularly long dry season. And then I think what's possibly missing here is getting a strong baseline as well. That's another driver for data collection. It's not just designing it's not just getting data to help design surface water management during operations. It's building a data set to understand any impacts that mining will have on the environment. So especially things like sediment and water quality, mining will cause release of sediment, but often that would occur under baseline conditions, especially in arid, semi-arid climates where you get a intense rainfall event and not much vegetation. Sediment's going to be mobilized, so it's important to have a strong baseline of data to be able to demonstrate that mining isn't having an impact in addition to what would happen naturally. So yeah, so this feeds on to monitoring is needed in the right places and at the right frequency. So again, that's as I said before, if the focus is on extreme flood flows, then you need monitoring at the frequency of sub-hourly, whereas if the issues identified in the conceptual model all relates to dry season water supply being the big problem, then there may be monitoring needed. Monitoring isn't needed at that sort of resolution, and that goes into it's the quality of the data and not the quantity that's important. So this is a good graph showing the black dots are stage board readings and also periods of flow measurement in a river, and the different colors show logger data collected in that time, and this is a river level data set on this graph. And you can collect, you can do a very good data collection at monthly or weekly periods and get flows and levels, which would be these black dots, but you can easily miss the peak flows. And again, if extreme flows is what is interesting to the site and what is going to define the surface water management, then this data set isn't particularly useful as just the weekly or monthly data capture, and something like a logger will need to be put in to collect the river level data. And it's just worth investing in that additional data collection. So rainfall, something like a tipping bucket rain gauge to get rainfall at a sub hourly resolution, a logger to get river levels at sub hourly to a few minute resolution, and then even as far as actually getting measurements of flow. So consider like normal using an impeller in a river, where you'd wade in, you can only do during low flows. So is it worth investigating, taking flow measurements during higher flows from a bridge, or installing a cableway, or even more sophisticated flow measurement technology like acoustic Doppler current profiler? And it may seem expensive, but the cost of this sort of data collection against using overly conservative design criteria on the infrastructure is tiny. Like, it will, if there's not the data to back up the design, then you can't, there's no other option but to use conservative assumptions, and conveyance channels and ponds will end up being oversized, and that's a huge expense. And the other thing to keep in mind is, it's all good to say you collect data for your needs, but the needs do change. So going back to the block caving example, when the mine first started, it might have only considered being an open pit, and then things developed, and more resource was found, and it's evolved into an underground mine. So having data collected that's maybe more than you needed at the time, there'll be no regrets down the line when it's there to do maybe more sophisticated assessments, because the mine design has changed. And finally on this, and not, to me, this is very this is key and often overlooked, is the opportunistic data collection. So this is sort of, I mean, as it says, it's taking advantage of opportunities to collect data that may not be part of the routine data collection plan. So things like after heavy rains, taking that opportunity to go out onto site, take lots of pictures, maybe try and identify where the high water level was in streams by, you might see debris lines or leaves in trees, or there's evidence of where the water level got up to, and even maybe getting a surveyor out to take that level measurement. And similarly, maybe during a particularly dry period at the end when it hasn't rained for a long time, getting out into the surface water regime and doing river or stream profiling, developing accretionary profiles to see the interactions between groundwater and surface water down the length of a river, identify losing or gaining stretches of river, take water quality samples down the river and field parameters, EC and things, and often it's these sort of one-off data collection exercises that can really underpin a whole study and be extremely valuable, even if it wasn't initially planned for in the management plan. And part of this is also anecdotal information. When out in the field at a sampling point, there may be a local member of the community nearby, and having a conversation. There's so much knowledge there that definitely on numerous studies, just members of the community have been able to identify, explain peak levels that they've seen in their lifetime, up to that top of that rock or something like that, or even, oh yes, this stretch of the river goes dry, it's happened twice in the last 20 years or something like that. And again, it's just so valuable, that sort of information. And I would say key to getting that opportunistic data collection is kind of making sure that everyone involved in data collection has an understanding of why the data is being collected, and understands the conceptual model, understands the questions that are being asked and need answers to, and so because it's the people on site and the people collecting the data that need to recognize these opportunities, because often people doing these analysis look at it every 6 months, every year, or even just a one-off, and opportunities are missed because the data is only looked at periodically. And so that sort of level of understanding through whole teams can really improve the quality of data that you get. And part of that is also allowing everyone in the team to feel empowered to react to opportunities. Maybe realize after a rainy day, like, oh, let's just cancel these meetings or change, rearrange these tasks we had planned, and let's go out because it's just been raining. Let's take lots of photos, take a few samples, take a few measurements. This will be really valuable. And that sort of understanding also results in a much better quality data set. The people involved, everyone collecting the data will really recognize when there are potential issues with the data being collected. So another example is at a gauging station in a river during the dry season. The people in the community would pile up rocks to pond water to use as a little water supply just by the gauging station, which would totally change the stage discharge relationship. But the whole team that manage that data, immediately recognized the impact that would have on the relationship, and could address it and take new measurements to make sure that seasonally the relationship could be changed, and saved a lot of data, rather than continuing to routinely take data but not recognize some of the issues. So typical requirements, collecting meteorological data, flow data, say weirs, loggers, pipeline flow meters, for example, volume data sets, bathymetry, elevation, with pond geometry, for example. These are all key data sets. And then chemistry, the physicochemical characteristics, suspended solids, turbidity, major ions, dissolved metals. That's key, but total metals are also useful, especially if there's some impact from sediment in the water sets, and nutrients, and also and also just another thing for data collection is depending on location, there can be some existing data sets that you can research or get from government data sets that really help. So analysis of this data, a very quick slide, but all this data goes into then multiple statistical methods can be used to turn this data into parameters that can be put into a model to get results to inform surface water management, from design to the full water balance. So for example, this is just using rainfall record to get return period rainfall events, but there's many more, and it's well covered in textbooks. So yeah, you have your data collected, you do the data analysis, and then you use that analysis to parameterize models. And models can range from very simple calculations to extremely complex numerical solutions. And it's often thought of the complex models is kind of what springs to mind, but very simple calculations can be just as valuable, if not more valuable. So for example, a simple calculation of flow, peak flow from a catchment, being a function of a runoff coefficient, the intensity of rainfall, and the catchment area. That's a model the rational method, and all the way up to a full 2 or 3 dimensional numerical solution, looking at, say, velocity and in flows to inform like a scour assessment. It really ranges from those 2 end members. But keep things as simple as possible. Yes, something like this may be required, if the data's there, and if that sort of resolution of information is needed. But if it's not, then something like this is always preferred. Everyone can understand it. It's easy to communicate. It's easy to identify if there's an issue. You know all the parameters, and you can look at the numbers and see if it makes sense. Something like this will have tens to hundreds of parameters, and it's difficult to kind of identify if there are any issues involved. And it's very quick to update and do like sensitivity analyses on, and ultimately just as valid. So yeah, I'll do my best with this slide showing, and this is kind of a way to try and look at modeling as on like a continuum, really. So from design of a single component of a water of a mine site system, like a conveyance channel, all the way to like linking all the different surface water components together for the full site-wide water management plan. So that's the objective, and how you do that. So we're looking at single event models, extreme event analysis, and a rainfall runoff model, just looking at one event to design one conveyance channel. and then all the way to linking, you know, yes, conveyance channels, but pit flows, runoff from waste rock dumps, and then water treatment requirements, water quality, and everything that goes into a water management plan. And that's, you're looking at like a full site-wide water balance model. And, you know, this will be a single event, you know, one day or a few day time period model, just looking at one rainfall event. And this will be more of a continuous, you know, could a model running over, you know, the whole of mine life and through closure. And then, you know, lots of other things fall around between these two extremes. So, you know, sediment pond design or flood risk assessment, you know, yes, it's mostly down to, you know, an extreme event, but actually, you know, antecedent moisture conditions are important, and you know, it could be, you know, end of wet season conditions over a longer period define the flood risk or peak sediment release. And even more continuous things like storage ponds and pump capacity designs and sump pumps, things like that. That's again, you know, at the end of a wet period rather than from a single event. So many moderate events would define the maximum size that you need for storage and for pumping rather than one single event potentially. And again, water supply even more, you know, you're looking at a full season, a full dry season, or you know, abnormally dry season that will define that. And you know, this is where like a water balance model can be used. You know, maybe you don't need a full site-wide model, but again, for the area of interest, you know, and you can look at average conditions or over a year or over a month to inform these sort of studies. And you know, you can look at run worst case scenarios through these water balance models just to see how bad it can get. And you know, things like the cyanide code compliance, like it's written into that code that you have to have a probabilistic water balance model. And again, on this edge of things, you know, you can start to trade off mine plans and evaluate things like water treatment and run different scenarios. And all this is key. It's just looking at everything together and how they all interact and the knock-on effects of changing one part of the system. So that brings us on to water balances. So, you know, it can have several meanings, but you know, often just a spreadsheet of flow meter records or a flow diagram is described as the water balance. But you know, they're useful data sets, but it's not a water balance. It's what they are. You know, these are useful data sets and useful information showing how different facilities link together, but they're not water balances. So a water balance, in the name, you know, has to balance. So, you know, it's a series of calculations that show that the inflows minus the outflows balances with a change in storage. So, for example, you could just build a water balance around a pit sump and your inflows being, you know, precipitation, runoff, and groundwater inflows, and your outflows being evaporation and pumping out of the sump, and the storage being the change in water level of the sump, and quantifying all of those and showing that they balance with each other. That's the water balance. So, you know, here, typical example, like inflows into this system, you know, precipitation, then you can have a groundwater inflow as well, and yeah, the runoff, direct precipitation into your ponds and runoff, and then other inflows. It could be water supply, could be a surface water supply or groundwater bore field, all entering the mine system. And then outflows, evaporation or recharge into ground that doesn't return elsewhere on the mine site. Yes, seepage from the storage, pumping to the plant as a water supply, spill to the environment, that flow's gone from the system, and even like water, bound within, say, tailings, like sequestered within tailings, that's an outflow. And then storage, the obvious one is where you can see it, the ponds, it could be a pit lake, it could be storage ponds, the TSF. That's clear, but also it's water stored, in the system in general. So, for runoff, there's a store of water within the soil zone, and after a dry period, that store is very empty, and you can get lots of rainfall won't generate runoff and will be stored within that soil zone, and then after a long wet period, that will be full, and all rainfall will kind of generate runoff. So a key thing to understand, and also things like waste rock dumps, that can take a lot of storage as well, and heap leach pads, rainfall onto those. There's lots of porosity to kind of hold that water, and understanding that the role of that storage with rainfall and then resulting runoff and seepage is also very important in building water balances. So they're used for a wide range of purposes. They can be facility specific, as discussed. You can just look at a pit or a process plant, and they can be useful for those things. Building a pit lake model, you can just look at one pit and the groundwater inflows and the surface water inflows and see how a pit lake will develop, and you don't have to think about anything else on site. But the key, the most value is these site-wide water balance models, and that's just linking the whole mine water management system, all the mine facilities, natural catchments reporting to the mine, and you find a lot of mine sites, there are excellent facility specific water balances. Maybe a process plant has one, the pit team has one, TSF team has one, but making them link together can really help improve the water management on site. The impact on the TSF if process change what they do, or if process change their if they have issues, a thickener is down, or if they change the milling rate. And they could be backward looking, so you can actually just build a water balance using actual reported data and use the water balance to back calculate unknowns. You can, but by generating a balance, you can isolate, say, what the groundwater inflow must have been for it to balance, because you've got a record of the surface water inflows, you've got a record of the evaporation, you've got a record of what's been pumped, and the imbalance in those terms must be made up by groundwater inflow, and therefore you can calculate that number. And then really useful is doing forward projections. So it can be short term. You can look at the start of a wet season, for example. You can input all the pond levels currently, run a short projection and see if there's potential issues for maybe not enough water or too much water over the next wet or dry season. And there's also a long-term planning for big decision making, TSF raises, or do you do a TSF cell, or treatment requirements, and all the impacts of you know, expanding mining, and then finally like closure simulations as well. You know, all the plans for closing the mine site, will that do the job in managing surface water on site? So for probabilistic water balance models, GoldSim is the industry standard, and it allows probabilistic simulation of dynamic and complex systems. It's a coupled, and what's great about it is it's not just flows and volumes, but you can link water quality to it. So it's the sort of complete package to assess, you know, surface water management on site from a quantity and quality point of view. And also what's great is dashboards can be used. So, you know, a GoldSim modeler can build the models, but almost anyone can use it to run simulations. And, you know, there's a player version of GoldSim, which means there's no need to download, there's no need to buy a license. It's free to use. So the model could be constructed, and anyone can change parameters and test different scenarios using the free player file using dashboards. So in terms of what drives a mine site water balance model, precipitation is the big one, and it's predictably unpredictable. So that's really why we use probabilistic water balance models. That's the probabilistic component, and evaporation, which is a bit more consistent. The surface area of a mine site, so the changing, you know, pit, TSF, pond and dump and leach pad area, which ultimately changes the sort of catchment area within the mine site of rainfall generating runoff, and groundwater inflows, what's going to come through in pits and underground, or borehole dewatering, and then the processing rates. So the mill feed, you know, most importantly affects how much water is sequestered, stored in the tailings and leach pads, and also, you know, general mining rates for waste rock dumps, again, another big store of water. So on to I mean, those are the main. There'll be others, but those are the four kind of key inputs that kind of pushes the water balance model. So in terms of modeling precipitation in GoldSim, you could take historic precipitation data, and, you know, you look at how many wet days there are, typical volume, typical amount of rainfall, and also look at extreme events for different return periods, and, you know, run a series of statistical analyses, and you can produce a precipitation generator that basically tests the system for statistically accurate precipitation events. And, you know, this is actual historic rainfall, the black line here, and then this is a projected rainfall, so, you know, it's more, this is a daily data set. It's more easy to interpret on a monthly scale. So this is showing monthly rainfall again. It's the same data set, but as a total monthly, and this is again the projected rainfall, and these colors show the envelope. Sorry, just struggling with yeah, they show the envelope of
Hello, Phil, are you there?
Yeah, so these show the probabilities of monthly rainfall distribution. So the yellow zone is the interquartile range. So there's a 1 in 4 chance that monthly rainfall will be within this area. The blue lines show that there's the 5th to the 95th percentile. So there's a 1 in 20 chance that rainfall will be of this magnitude, and then all the way up to the 99th percentile is this gray area. So these are sort of the extreme rainfall possibilities. And it's clear from this that this 2019-2020 year was actually a wet year, and it's falling in the sort of 1 in 20 year wet year range. So this is like this is just sort of give an idea how a water balance might change. So this is the footprint area of the mine site combined. This is the groundwater inflow, and this is the mill feed, and this is the resulting water balance. So the orange is the runoff generated from the footprint area, and that's an inflow, so that's positive. The green is water lost to evaporation from ponds or from surface, and then the grey is water lost that's sequestered within the tailings generated from the process circuit. So at the very beginning, when there's no mill feed and there's no groundwater inflows, but there's a catchment area, you have a positive water balance because there's that flow to deal with, and there's no losses other than all that flow has to be discharged from site. And then as the mill feed increases, the amount of water stored in tailings increases, and actually you can get almost a neutral water balance. So the flow generated from site is the flow generated from rainfall runoff is used in process and then stored in the tailings. And then as the pit develops, a groundwater inflow starts to occur, and there's a good balance between the surface water inputs and what's lost to tailings, but this groundwater inflow pushes the overall balance more positive. And again, you might have an expansion, the pit expansion, and it's again it pushes the water balance even more positive. And again, deepening of the pit, increases groundwater inflow, but then you might have a mill expansion, so more flows are locked up in the tailings, and it brings the water balance down again. So you have the increasing positive water balance, and then it gets brought down. And then a pit might be closed, but you still have the same mill feed because part of the pit's just been rehabilitated and sent off to the environment. And suddenly there might be a negative water balance, and there's not sufficient water in the system to supply process, and consideration of getting a water supply from elsewhere is suddenly needed. And then again, as the mill feed decreases and less water is lost in the tailings, then the water balance becomes increasingly positive. And the big thing is in closure, when you got no mill feed, then actually that really can push the water balance positive, and shouldn't be overlooked, and is often a big consideration. And And another thing to consider, again, with underground, especially in block caving, it may be a requirement to keep all the facilities open, including the open pits, and that generates a very big footprint area and a very high groundwater inflow. But with the underground, abstraction rate, the mill feed could go right down, and that can really push the water balance into a positive direction. And some examples of how the water balance can be used. Evaluation of emergency response plans. So here's an example of a pond spilling that you don't want to spill because it's contact water. And this is at the 50th percentile rainfall event, so 1 in 2 year probability. And at the 50th percentile, without any plan or control, the surface water will spill. But you could put in a trigger action, a response, and to divert flow, say, to the pit at 1 meter freeboard, and that means that there's no spill, and you can test that in the model. But then you can then test it for a more extreme event, and this shows here that with nothing in place, you get a significant spill. If you divert water to the pit at a 1 meter freeboard, it doesn't actually help you that much for extreme flows, and you need to increase the freeboard to about 2 meters to bring down that spill level, and maybe further to bring it to 0. So again, it's all just a tool to assess risk and to test different options in managing water and the effects. And what's key is always getting around the table and discussing these and understanding the risk against the cost of in this case diverting water to the pit. Here you can see the effect of taking a thickener offline for 6 months from process and sending more water to the TSF, because there's the slurry is much reduced percent solids, and the green is if the thickener wasn't taken offline, and the red is with the thickener taken offline. And you can see that the it shows the volume on the TSF is manageable and it's okay, but as long as more reclaim can be sent back to the plant from the TSF. Now, this assessment might, the reclaim infrastructure may only be able to have a maximum of 250 litres a second, in which case this won't work, and this would inform maybe the need to increase potential pumping from the TSF in case there's an issue with the thickener at the mine site. And again, an example of potential shutdown from COVID. If process is shut down and there's no reclaim needed, and it goes down to 0, and basically there's no flow out from the TSF, and rainfall is allowed to build, you can quantify what the effect of that, and then start to talk about, are there issues with this build, and can water go up to 1 million meters cubed? Is that acceptable? And or if we were shut down for 6 months, is that where we really get critical? So it's a really useful decision-making tool. And this is, looking at water treatment. So this is great for just like optimizing systems on site and making them as efficient as possible. You can see with no treatment, there's an annual positive water balance, and a pond fills and begins to spill. You can then assess what happens at the pond if you do a treatment at 25 meters cubed per hour. You can see it helps massively, but there are still incidences of spill. And if you increase it to 50, then it's fine. You don't have any spill. But then in addition to that, you then look at optimization of treatment, and here you can't even see the line. It's at 100% pretty much at the 50th percentile utilization of treatment. So you're showing that treatment would be constantly pumping at 25 meters cubed per hour to manage a pond like this. Whereas if you increase it to 50 meters cubed per hour, during periods, the plant utilization drops right down because there just isn't the water to be pumped at such a high rate. It's not coming into the system. So it's a trade-off of all these things, and you know, ideally you know, in an ideal world you'd set the treatment rate at the excess flow rate coming into the pond, and then there would be sufficient storage to buffer out the seasonality. And so the treatment would essentially be 100% utilization, and then, you know, during periods of high rainfall the storage builds up, and maybe if you had like a pit that you could use to put water in, you know, that's possible, but often it's not. So, you know, you can look at all kinds of things with the GoldSim model to optimize what you actually have. So if the storage is set, then, you know, maybe it could be pumped to a lower level during the wet season to bring up optimization, or maybe linked with water quality again during the wet season, that the inflows, because of the high rainfall amount, the inflows, the water quality is quite good, and therefore the flow, some of the flow can be bypassed around treatment, and therefore this 25 meters cube per hour feed may work during the wet season with bypass. Or maybe you can have 50 meters, assuming the units of treatment are only in 25 meters cube per hour. Maybe you know, seasonally you can have 50 meters cube per hour feed, and then a treatment unit can be shut down, and then in the dry season just have 25 meters cube per hour running, and then again, you can, at a click of a button, you can look at it at different resolutions. So this is utilization at a annual level, and you can see over a year it's utilized, you know, at the 50th percentile, about 85%. And then mine water quality management, you know, again, you can just run different scenarios. So this shows a high sulfate pit water going to a pond, and, you know, your sulfate limit may be 1,000 milligrams per liter, and it's showing exceedance. You know, this water would have to be treated. But if you send that high sulfate water to the process plant instead, then maybe the water quality in the pond would be much improved from the other sources, and this water could be discharged. So, you know, different scenarios can be run to optimize treatment and optimize which water's used where, which water's mixed where. And then, yeah, so to sum up, clearly define the question that you want to answer, which is based on the conceptual model, and looking at and it's key to, you know, conceptualize the system, look at the data, and constantly reevaluate, and understand the risk tolerance, and, you know, what you need to design for, and where you really need to be sure that the management works, and then use appropriate tools to do that. So, you know, keep it as simple as possible, use complexity where needed, but ultimately, you know, keep it simple and where you can. So thanks very much, and apologies for running over time. I'll hand back to Eduardo.
Thanks, Phil, for your great presentation. So if anyone has any questions, please.
¿Alguno tenéis alguna pregunta? Que sé si queréis la hacemos en español y la traducimos.
Hay gente vergonzosa hoy.
Lo podéis hacer por el chat si no os atrevéis a hablar.
So at least from my side, Phil, there is an understanding of an hydraulic balance sometimes at the beginning we'll use to understand what is the all of the sources of water and the requirements from the operation, understand what's going on when a consultant arrives to a mine, and try to improve the use of contact water into the process plant and etc., and try to reduce the discharge. So to make that work, to understand what are the sources of water and what are demanding, and understanding what will be the future mine plan and the requirements of expansion of open pit, underground mine, and the total volumes of water that will be generated, can help to understand the main risks for the operation and the requirements for treat water, and try to achieve all of the discharge permits. So after that, to pass to a numerical model as GoldSim, as we realize in several projects, is a very useful tool. But as you said, try to maintain as simple as possible, because sometimes we want to use very complicated formulas or complicated circuits, and then it's very difficult to calibrate that models. So in your experience for chemical mass models, what are the most challenging issues to try to manage in a GoldSim model to try to calibrate and have a good results?
For the chemical mass balance, then I'll probably say the biggest challenge is that GoldSim is very much a mixing model. So all the elements and parameters are conservative and it's mixed, whereas in reality the resulting chemistry is pH dependent, thermodynamic reactions. So it's GoldSim can handle those things, but you have to input them, and it's the analysis outside of GoldSim that's probably the challenge to put in the correct factors to make GoldSim model the mass correctly and calibrate that. The flow side is more straightforward.
And in your experience, there is any option to link GoldSim model with other models as FreakC, something similar, to try to manage what the geochemical analysis provide for, I don't know, filtration from wet rock dams or TSF, and including this in the GoldSim model?
So it has been done. You can link GoldSim to FreakC. The one word of caution with that is with FreakC, there's a strong requirement for someone who's from that geochemical background to look at the results and make sure what is being output is correct. So it's with each use of FreakC, ideally you really want to review it and look over it with a knowledgeable eye. So allowing a model to consistently input into FreakC and pull results out, there's a risk that an error can compound with time and get out there. So it definitely can be done. A better way is having a strong geochemistry team look at relationships, and then you can develop factors that can then be input into GoldSim to manage those sorts of reactions, and that's much more robust way of modeling.
Well, thanks.
I say.
Bill, Adriana Sanchez here. Thank you for the presentation. I have a question. How do you think we can manage, which one is the best way to manage the uncertainty in the conceptual modeling and in the numerical modeling? I mean, for example, in the uncertainty in the operational point of view, for example, infiltration on ponds on the pit, and the technical uncertainty too. For example, the uncertainty in the recharge, specifically in in dry areas, as here in Chile, for example, in the north of Chile, karst areas, preferred flow through structures and something like that. How do you think we can manage this uncertainty in our modeling, the operational one and the technical one?
So yeah, that's a great question. So in GoldSim, it manages an uncertainty probabilistically. So as we use it with the rainfall as the main area of uncertainty and run it probabilistically. So you can add uncertainty for all those other parameters, but what happens when if you do that, then the results will be over such a big spread that they're almost unusable because you're just showing a big envelope of uncertainty. So for those sorts of things, I would stick with the probabilistic modeling with rainfall as the only probabilistic input, but run different model runs. So create different scenarios and pick the two maybe extremes end members. So run a scenario with your minimum recharge rate, where you're uncertain of that recharge rate, and then run it again with the maximum, and then compare the two. And I think that will allow you to much more clearly demonstrate the uncertainty that's a result of the recharge rather than uncertainty as a result of the rainfall. And you can do that again with other areas of uncertainty to sort of get your two extremes, and then based on those results, can then inform you whether it's worth going out and doing further studies to reduce the uncertainty in those parameters.
And only one thing to add to what Phil mentioned, and from a question from Adriana for Chile. So a GoldSim model, at the end, the uncertainty in some aspects of, I don't know, filtration from weather dams, TSFs, or inflows from the open pits or underground mines, will be taking the information that come from the different numerical models. So maybe a numerical hydrodynamic models for the weather dams and the TSF that also in the sensitivity analysis will take into account the changing parameters as hydraulic conductivity or recharge, taking into account in Chile as, say, a guideline included recently the climate change also, and for to take into account the inflows into the pit, also extract information from the groundwater model, mud flow, free flow models. So, and run the sensitivity analysis that also the GoldSim model will take into account, and run this sensitivity analysis according to the future mine plan. So I hope that, Adriana, answer your question.
Yes, thank you for the answer. I think it's a really interesting conversation, the uncertainty management, and how to do sensitivity analysis and uncertainty analysis. It's a tough question, I think.
Yeah, and as you say, in Chile, and in our experience, is a good country to address your question, because as you know, the SEIA and DGA and etc. Taking into account the numerical models in a lot of detail and asking all of the consultants to run a range of sensitivity analysis and demonstrate that this range of changing parameters in hydraulic conductivity, storage, recharge, consistent with the information collected on the field, and in a good range. And also recently include that climatic change that we need to take into account in the future to know if we will have more rainfall or not, and include that other question in all of the results from the models. So that's a good country to discuss all of the project related to the environmental impact studies. So thanks.
Yeah.
Any other question? From my side, in one project that I work with Phil in Spain, we use the hydraulic balance and use GoldSim to address 3 main points for one mine. It's only to make an idea of how this hydraulic balance and GoldSim model can help mines and operating mines. So we analyze the problem of discharging to achieve the discharge parameters, and we analyze what is the contact water generated and the contact water they can use in the process plan, and try to run different scenarios in the future, and at the end give to the mine a solution that pass for different phases, but one is maximize the consumption of non-contact water in the process plant, reduce the storage in the TSF, because at the end this water will increase the concentration of different elements that will be impossible to treat at the closure of the mine, and help in the design of the expansion of the water treatment plant. Only taking the information from the latest years, analyze the flows and the concentration from the different sources, and produce this predictive scenario that Phil explained. And with this range of probabilities we have, we propose to the mine different options to reduce that issue and try to achieve the discharge permitting. So that's one of a lot of projects we are working and using GoldSim, but at the end, with few time, we can demonstrate to the mining companies and to the authorities also that something very simple and investing not a lot of money and on time, we can achieve the main issues of the mine, managing contact waters. So that's all. So if you don't have any other question, Carlos, pass to you. You are on mute.
Sorry, no. Related to understanding the risk tolerance, well, would you have been providing a certain pump output while using pumps? Do you have a certain amount of pumps to be used as a backup in the event of any failure of the pumps you are using? So when you have to achieve a certain flow rate, do you have any backup as a proven risk tolerance acceptance in your operation? Thank you.
Yeah, no, that's another great question. I think that's what the water balance will be used for, is to tell you the consequence of if you have a pump failure. So you know, you'd start off just assuming you have one pump doing the job. See what happens if a pump has failed for 1 day, 2 days, 3 days, and then if the consequence of that in the model shows that, you know, you'd have operational downtime for weeks, then that would tell you how many, you know, how many more pumps to purchase as backup. So you may need 1 backup pump, or, you know, 2 if it's really expensive to have the downtime. But the other thing it will tell you is the flow magnitude from the sump. So and sometimes you know, the flows can be extremely variable across the wet and dry season, and you know, you just don't want one big pump to deal with the extreme flows, because it will be run at such a low rate that it won't be efficient. So the model will tell you that it's more efficient to run, you know, 5 or 6 pumps and only a few of them at a time, and that will kind of give you capacity as well to have, you know, reduce the risk of pump failure. You know, 1 pump being down isn't as big a issue as if it's a small pump of many than 1 large pump being down. So all this comes out of the model, really.
Yeah, I'm asking you, so if you're in a remote location, which you are far away from the place, if you need some spare parts or whatever, So you have to be quite confident on how the pump is working, because otherwise, say, imagine you're in the middle of, say, Argelia or in the middle of Mauritania. Well, probably in Argelia, Mauritania, you don't have a lot of problems with the water, unless you have finding that underwater. But say if you're in the jungle or any other places where you're far away from where the spare parts are, so probably you will be providing with a spare part to function in the event of any failure. So then there will be, assuming no risk at all, but it will be quite costly if the water is not controlled, isn't it?
Yeah, exactly. And especially, you know, yeah, in some remote areas, you know, access can be cut off to bring in replacements during the wet season when you most need them. So, you know, yeah, in those factors need to be considered, and you know, you may have way more belt and braces, you know, backup system, just to make sure that there's no chance of the pit not being operational for weeks or months.
Well, thank you very much. Well, I would like to thank Phil Benghiat for his nice presentation we have today, and quite profitable. And on behalf of our institution, Colegio Oficial de Geólogos, we thank you very much, Pito Associates, Phil and collaborators, and we hope to see you soon again to share your presentation either in the European Federation of Geologists, and if we have the chance to repeat these interesting presentations with our colleagues, we'll be glad to have you in our house. Thank you very much for your cooperation, Phil, and thank you all for attending this webinar series presented by the Colegio Oficial de Geólogos. Thank you much and good afternoon.
Thank you very much.